gears, they're everywhere. The unsung workhorses, really, of almost every mechanical system we rely on. I mean, think about it from tiny watch mechanisms right up to massive industrial plants. They're absolutely essential, silently doing their job, transferring power, transferring motion, often completely hidden from view. But here's the thing. Despite being so fundamental, so ubiquitous, there's this critical paradox. Gears are, well, incredibly susceptible to wear and tear. They break down. So today we're doing a deep dive into exactly why these critical components fail. We'll explore the cutting-edge solutions emerging and how engineers are pushing the boundaries, really, of material science and manufacturing to make them last longer. Our insights for this discussion come straight from a really detailed technical article. It's titled Fenomeni di danneggiamento delle ruotentate. That's Italian for gear damage phenomena by Giorgio De Pasquale and Elena Perotti, published just recently, July 24, 2025. So this deep dive, it's going to take you on a bit of a journey through the intricate mechanics of gear failure, the state-of-the-art diagnostic methods being used now, and some truly exciting innovations in materials and manufacturing, including the incredible potential of, well, 3D printing. And look, this isn't just for engineers listening in. Understanding the longevity, the reliability of mechanical systems, it impacts pretty much everything. From the cars we drive, their smooth operation, to the precision needed in life-saving medical devices, right through to the huge industrial production lines powering our economy. It's all about minimizing costly downtime, enhancing safety, and just ensuring modern life runs smoothly. Okay, let's unpack this. We often just take gears for granted, don't we? They're so fundamental, they just sort of fade into the background. But they are, at their core, these essential structural components. Their whole job is transferring movement and power in, well, pretty much any mechanical system you can think of. Their design, their integrity, the materials, it all directly influences efficiency, precision, performance, and crucially, the reliability. Not just of one device, but of entire complex systems.
Absolutely. Think about a robot arm on an assembly line needing perfect timing, or the smooth acceleration of an EV, or the precision of a surgical tool. Gears are behind all of that, needing to perform flawlessly.
Yeah, exactly.
And it's fascinating, isn't it, how foundational they are, yet, as you said, how vulnerable they can be. They face this really complex array of stresses. These parts often operate in what the source calls hostile environments. They're subject to a critical combination of factors, all happening at the same time.
Hostile environments. What does that really mean in practice?
Well, we're not just talking one or two challenges. It's this constant onslaught.
Yeah.
Heavy loads, high speeds, sometimes at extreme temperatures, humidity, corrosion eating away at surfaces, and even something often overlooked, poor lubrication. Each of these, on its own or together, makes gears really prone to various kinds of damage and fatigue.
Right.
Just picture a gear inside a wind turbine, spinning for years, battling the elements. Or one deep underwater in a submersible, under immense pressure, corrosive salt water. It's actually a testament to engineering they last as long as they do. But it also highlights why failure is, well, pretty common.
And when we talk about common damage types, the article mentions two specific ones right away: pitting and micro-pitting. For listeners who might not be deep in mechanical engineering, what exactly are these, and why are they such a headache for designers?
Okay, so pitting and micro-pitting. Think of them like tiny potholes forming on the surface of a gear tooth. It's a surface fatigue process. Pitting happens because of the repeated stress from teeth meshing together. This starts tiny cracks below the surface. Eventually, these cracks work their way up, and a small piece of material breaks off, leaving a literal pit.
Okay, like a little crater.
Exactly. And micro-pitting is, well, a microscopic version of that. Much smaller surface cracks, often giving the tooth flank this kind of dull, frosted look. Both are bad news. They're critical design challenges because they mess up the smooth operation. You get more friction, more noise, and ultimately the gear just doesn't perform as well, and its life is cut short.
And once they start...
Right, once those pits form, they act as stress concentrators. They make the surrounding material even more likely to fail, so the damage just accelerates.
So it's definitely not just a minor issue. The estimates mentioned in the source are pretty stark, actually. Gear damage is apparently the main cause of failures in mechanical transmission systems. Think about that domino effect. One small gear fails, and it can cascade. Big system failures, unexpected costs, delays, even safety risks. It's not just a broken part, it affects the whole operation.
Precisely. And it raises that crucial question. What factors really drive these failures across the gear's whole life?
Yeah, what influences this?
Well, it's rarely just one single thing. The factors are incredibly numerous, and they span every single phase of a gear's life. We're talking decisions made right back at the initial design stage. the precision or maybe lack of it in manufacturing, how carefully it's assembled, and then everything that happens during its actual use out in the field.
So from cradle to grave, essentially.
Exactly. Take material selection. That's not just a technical detail. The source calls it a strategic decision.
Strategic, how so?
Because the material choice directly dictates things like load capacity, wear resistance under different conditions, overall efficiency, and ultimately, its useful life. If you choose the wrong material for the job, you're basically setting it up for premature failure, unexpected maintenance nightmares, and higher operating costs that just ripple through everything. It's absolutely foundational.
And it seems like getting the design and manufacturing right isn't the whole story either. The source really emphasizes this need for best practices after the gear is made and installed, during operation and maintenance.
That's a critical point. Optimizing design or production or installation, that's not enough on its own for longevity. You need these ongoing best practices throughout the entire life cycle.
So what does that mean practically? What's the big shift needed in how industries approach maintenance? Is it just reacting less, preventing more?
It's exactly that. It's a fundamental shift away from the old run-to-failure model.
Yeah.
Just wait for it to break. Or even just scheduled maintenance, replacing parts, whether they need it or not.
Right, which can be wasteful.
Very wasteful. Instead, the focus now is on truly predictive strategies, embracing things like condition monitoring CM and proactive program maintenance. It means being constantly vigilant, setting up regular inspections, using smart tools to anticipate failures before they happen. This is absolutely essential in industry to minimize that unplanned downtime, which can mean huge production losses. It's about improving safety and reliability together.
So not just fixing, but predicting. Okay, that leads us perfectly into the next big topic. This proactive defense using fault detection and condition monitoring. What are the traditional ways we've done this?
Right, the traditional methods have been the backbone for a long time. They give us critical info about a failure once it starts showing signs. These methods are basically about listening to the machine in different ways. Vibration analysis is a big one, listening to the shakes and tremors.
Like a stethoscope for machines?
Kind of, yeah. Then there's oil analysis, checking the lubricant for wear particles or degradation. Temperature analysis, looking for hot spots. Energy analysis, checking power consumption. And acoustic emission detection, picking up high-frequency sounds from things like crack spreading.
And among those, vibration seems particularly key.
It is. Vibration data is incredibly rich. It gives you immediate insights into the dynamics, the health of the system. So it's really well suited for enabling that predictive approach we were talking about.
But here's where it gets, well, really interesting, as the source points out. Recent advances in computing power. They've been huge, almost exponential. And this has led to the widespread use of artificial intelligence, AI, especially deep learning algorithms. This isn't just a small tweak. AI is fundamentally changing the game.
Oh, completely. It's transforming how we monitor and maintain these systems. AI isn't just supporting human analysis anymore. It's actively implementing and automating condition monitoring, CM, and structural health monitoring, SHM.
Automating it.
Yes. Imagine a system constantly listening to the machine, processing vast amounts of data, spotting patterns too subtle or complex for a human analyst, flagging potential issues long before they become critical.
That sounds incredibly powerful.
It is. It's a massive shift towards true predictive power. And that vibration data we mentioned, it's perfect for training these AI algorithms because it contains so much information about the system's properties and health. It's like giving the machine a voice that AI can understand, letting us intervene with surgical precision.
And connecting this to the bigger picture, the source talks about dynamic modeling and AI integration being revolutionary, especially things like digital twins. How do they fit in?
Digital twins, yeah. They have the potential to completely transform real-time monitoring. Picture a virtual replica of a physical gear system.
A digital copy.
Exactly. Fed constantly with real-time data from sensors on the actual gear. This twin can simulate stresses, predict wear patterns, even anticipate failure modes based on current conditions and past data. These strategies are highly sophisticated. They integrate real-world tests, dynamic modeling simulating how the system behaves under load data pre-processing to clean it up, and machine learning to analyze patterns and monitor wear with amazing accuracy.
So proactive maintenance becomes a real-time thing.
Precisely. Not just a goal, but a real-time capability. Industries can optimize performance, prevent downtime with a level of foresight that was, frankly, unimaginable before.
And that real-time insight is critical because acting fast when a fault starts is vital. What are the very first signs of trouble these systems look for? How do subtle problems escalate?
In those crucial early stages, The analysis often focuses on tiny changes at the tooth contact point, and it's something called transmission error.
Transmission error.
Yeah, even slight misalignments or other factors can cause localized stress concentrations where the teeth mesh. Think of it as tiny areas getting squeezed too hard, too often. This can quickly lead to microscopic surface cracks starting. And what often comes with those cracks?
Vibrations and noise.
Exactly. They're often the first audible clues, the telltale signs something's amiss. As things progress, deviations from the ideal tooth shape or oscillations in the shaft increase the risk of fracture and fatigue failure. And if you have severe misalignments or stress concentrations that aren't dealt with, they can dramatically speed up crack growth. That compromises performance and risks sudden catastrophic failure. Could shut down a whole production line or worse.
It really sounds like we're entering an era of smart diagnostics. How are these advanced techniques evolving to give us even more detail?
That's a great way to put it. These advanced diagnostic techniques are really emerging now. Recent experimental methods can actually simulate transmission error and contact characteristics even before a fault fully develops. They analyze how the load is distributed during meshing, pinpointing where stress is building up. By combining real-time vibration analysis, precise stress detection, other technologies, they can identify and predict faults with remarkable accuracy.
How? What's the key insight?
The key insight is that when a system starts to fail, there's a measurable change. A change in the energy distribution and the frequency components of its vibration signal. It's like a subtle shift in the system's voice. Extracting those characteristic fault signals, figuring out what they mean, that's done through increasingly sophisticated signal processing methods.
Okay, and the source breaks down those signal processing approaches into two main types. First, the traditional methods, mathematical signal processing, time domain, frequency domain. Can you give us a quick sense of those?
Sure. Traditional methods are rooted in classic engineering. Time domain analysis looks at the signal directly over time, spotting changes in amplitude or duration. Frequency domain analysis uses techniques like FFT, fast Fourier transform, to break the signal down into its different frequencies. You can see harmonics, identify specific frequencies linked to components or faults.
Sounds powerful, but maybe complex.
It is powerful, but yes, these generally need deep knowledge, high signal understanding, and significant practical experience from the analyst to interpret correctly. It's a bit like being a master artisan, relying on honed skill.
Okay, contrast that with the second category, intelligent diagnostic technologies, mostly AI-based. These seem to offer huge advantages in automation and capability. How do they compare?
The contrast is pretty stark. These AI-powered technologies are a massive leap forward, mainly through automation and their ability to handle complexity that traditional methods might struggle with. They're highly effective for building robust diagnostic models and processing incredibly complex, high-dimensional data sets, stuff that would just overwhelm a human.
So the AI does the heavy lifting.
In a way, yes. Instead of a human manually extracting features and applying rules, AI algorithms, especially deep learning models, can learn these features directly from the raw data. This makes them incredibly good at finding subtle, nonlinear patterns that signal early-stage faults. The source mentions four main types: artificial neural networks, ANNs, for pattern recognition; supportive vector machines, SVMs, for classification; convolutional neural networks, CNNs, great for time series data like vibrations; and deep belief networks, DBNs, for learning hierarchical data representations.
Wow, so that's why it's a major research focus.
Absolutely. It promises faster, more accurate diagnosis, and crucially, less reliance on constant human oversight.
So even with all this amazing progress, where does research need to go next? The source notes that optimization and integration of traditional methods with these advanced deep learning technologies is still a challenge. Why is bringing them together so important yet difficult?
It's crucial because, well, both approaches have strengths and weaknesses, right? Traditional methods offer interpretability, you can understand the physics behind the diagnosis, but they need expertise and struggle with massive data volumes. AI, especially deep learning, excels with that huge, complex data, finding hidden patterns. But sometimes it acts like a black box. It gives you an answer, but it's hard to know why.
Okay. The black box problem.
Exactly. So the challenge is creating hybrid systems. Systems that leverage the strengths of both. Maybe use AI for the initial sift, flagging anomalies, then bring in targeted traditional methods for deeper, interpretable investigation, or vice versa. Integrating them as complex needs seamless data flow, robust algorithms, ways for human experts to guide the AI's learning. The ultimate goal is a diagnostic system that's both incredibly powerful and transparent, giving you not just the what, but the why.
A fascinating challenge. Okay, so we've covered detecting problems early and the tools doing it, but let's shift to dissecting what actually goes wrong with a gear. How do we classify these failures? What's the worst that can happen?
Understanding the failure mechanism itself is absolutely key to prevention. The source outlines how damage phenomena can be classified into different categories. The main causes of failure include things like general wear, gradual material loss, partial seizure, or gripping surfaces momentarily sticking, plastic deformation, changing shape permanently without breaking. Then there's surface contact fatigue damage like the pitting and micropitting we discussed, cracking small fissures that can grow, and finally, fracture and bending fatigue where the material just breaks completely due to repeated stress.
And among those, fracture sounds like the really bad one.
Unquestionably. The source singles out gear fracture as the most severe failure mode. When a gear fractures, it often causes immediate extensive damage to the whole system. Catastrophic breakdown, not a slow decline.
And with fracture, it's important to differentiate between static and fatigue fracture, right? One sounds sudden, the other more gradual.
Exactly. That distinction is vital for diagnosis. Static overload fracture happens when a gear tooth gets hit with a load that's simply too much for the material strength. It deforms plastically, then snaps.
Like snapping a twig.
Pretty much. You could be ductile deforming a lot first or brittle snapping suddenly. Depends on the material. But fatigue failure is more insidious. It happens under lower loads, but there are cyclic repeating stresses. Not one big hit, but lots of smaller ones.
Okay.
Over time, these cyclic stresses start microscopic cracks, which slowly grow. They weaken the material bit by bit until the remaining part can't even handle the normal operating load anymore, and boom, complete fracture. Interestingly, the source knows that often a crack started by an impact, even a small one, can slowly turn into a fatigue crack. And sometimes you see signs of fretting corrosion near where it started.
Fretting corrosion, what's that?
It's a specific type of wear and corrosion that happens at the contact points between materials under very slight relative motion, like tiny vibrations. It can produce fine debris and actually help initiate cracks. It's a subtle clue in the forensic analysis.
So figuring out why a fracture happens sounds like real detective work. What factors influence it, and how hard is it to find the root cause?
It is very much like forensic science for materials. The factors influencing fracture can span that entire life cycle we talked about, making root cause analysis pretty complex. Often it boils down to errors made way back. Faulty design choices, using the wrong material, defects introduced during production, mistakes during assembly, or even just improper operation or bad maintenance later on.
What are some typical culprits?
Things like increased bending stress, maybe from misalignment or overload, non-metallic inclusions in the material acting as weak points, defects from heat treatment, messing up material properties, manufacturing flaws like surface scratches, and definitely excessive vibrations creating unexpected dynamic loads.
And this complexity, it means the gear failure is often linked to other problems in the system, right? You can't just look at the gear alone.
You've absolutely hit the nail on the head there. It's impossible to understand fracture just by looking at the gear in isolation. You need a system-level approach. A gear doesn't work alone. It's connected to shafts, bearings, the lubrication system. A bearing failing could cause shaft misalignment, which puts extra stress on the gear, leading to fracture.
Ah, I see.
So if you only looked at the broken gear, you might miss the real root cause, the failing bearing. You have to analyze the whole transmission system to truly understand why it failed and how to prevent it happening again, system-wide. It's seeing the whole picture.
Given that complexity then, what's the actual step-by-step process engineers follow when a gear breaks? Where do they start the investigation?
Okay, the detailed analysis starts with context, always. Understand the system the gear came from. What were the forces like? Lubrication type and condition. How long was it running before it failed? At the same time, you gather the gear's basic specs. Number and shape of teeth, the heat treatment used, required hardness. This initial data sets the scene.
Okay, context established. Then comes macroscopic observation. Just looking at it.
Pretty much, yeah. It's the initial visual inspection, maybe with a magnifying glass. You're doing a visual autopsy. Observe the general characteristics. Damage distribution, one tooth, multiple teeth. The fracture morphology, its shape, appearance. You're trying to identify the fracture position, where it seems to have started, how it's spread across the material. Looking for obvious clues, impact marks, clear progression lines.
Then you go deeper with microscopic analysis. This sounds like where the real clues lie. What tools are used here?
This is where we get down to the nitty-gritty. First, usually a stereo microscope, then the powerhouse. Scanning electron microscopy, or SM. With a stereo microscope, you look closely at the fracture surface edges, the color. Darker areas, maybe showing oxidation or rubbing, are often preliminarily tagged as the source area where the crack likely started. We take lots of pictures here to document everything.
And the SEM, what does that show you?
SM takes it to a whole other level. It lets us see the microscopic landscape of the fracture surface in incredible detail. We're hunting for features invisible to the naked eye. Tiny non-metallic inclusions within the material, the intricate texture of the fracture edges, subtle discolorations hinting at corrosion, characteristic arcs or patterns, and crucially, those telltale fatigue bands or striations. They're like growth rings on a tree, showing the step-by-step progression of a fatigue crack. They tell you how fast it grew and often point right back to the origin.
Wow.
It really is forensic science for gears, meticulously piecing together the story of its failure at an incredibly fine level, revealing defects maybe present since day one or damage incurred during service.
Okay, we've thoroughly dissected failure and diagnosis. Now, let's pivot to the innovation frontier. Polymer and hybrid 3D printed gears. This is where things get really exciting, isn't it? It really is. Additive manufacturing, or AM, 3D printing has been a genuine game changer across so many industries, and gears are definitely part of that. It offers some big advantages over traditional manufacturing. For starters, it can produce really complex shapes as single units. No joints, no assembly needed, which can be great for structural integrity.
Right. Less assembly often means fewer potential failure points, too.
Good point. Plus, it can lead to lower production costs, especially for small batches or custom designs. Less energy used compared to machining material way. And generally leaner, more agile manufacturing. But it's not perfect, right? The source mentions limitations.
Correct. Precision and surface finish are still areas needing careful attention. Getting the super smooth surfaces and tight tolerances needed for some high-performance gears can still be challenging with some AM processes. Research is ongoing there.
Still, despite those limits, 3D printed gears are becoming a valid, efficient alternative for certain applications. More and more, it seems.
Definitely. The performance, though, isn't automatic. It really depends on a combination of factors. Which specific 3D printing technology you use, FDM, SLA, others, what printing parameters you set, and of course the materials themselves. Getting that combination right is key.
And within 3D printing, polymer gears seem to be really taking off, especially in areas like mechatronics and medical devices.
Yes, they're seeing increasing use there. Polymers offer compelling advantages over metal gears in certain contexts.
Like what?
Well, significantly lower weight, for one, crucial in robotics or aerospace. Lower friction coefficient, meaning less energy lost as heat. Many polymers are self-lubricating, which simplifies design and maintenance. And often, lower production costs, especially for intricate designs. Plus, a big one for many applications. Polymer gears can absorb shocks and vibrations better, making things run much quieter. Huge plus in hospitals or offices.
Can they work with metal gears?
Yeah, the good mechanical and tribological friction and wear properties of engineering polymers like POM, polyoxymethylene, PA, polyamide like nylon, or PEEK, polyether ketone, mean they can actually mesh effectively with metal gears. Creates hybrid possibilities. Though, interestingly, the surface quality of the metal gear really affects how the polymer gear wears. A rough middle surface will chew up the polymer faster.
And does it matter how the polymer gear is made? Injection molding versus 3D printing?
According to the source, not fundamentally for wear behavior, whether it's molded, cut, or printed. The basic wear mechanisms tend to be similar for a given polymer. That gives a useful baseline for comparison.
But polymers aren't a magic bullet. They have significant limitations, don't they? Mainly around temperature and load.
That's the main trade-off, yes. High temperatures are their Achilles heel compared to metals.
Why is that?
At higher temperatures, the polymer structure changes. Mechanical properties degrade, load resistance drops where behavior gets worse. A gear happy in a cool environment might just melt or deform if things get too hot. They also generally have lower thermal conductivity. They trap heat easily. And higher thermal expansion, they change size more with temperature, which can cause misalignment.
Any other downsides?
Some polymers, like polyamide, absorb moisture. This makes them swell and can reduce their strength. So you really have to pick the right polymer for the specific operating environment, temperature, humidity, load. Get it wrong, and failure can be rapid.
Okay, so given those sensitivities, how do polymer gears typically fail? What are the common breakdown modes?
The source lists several specific failure modes for polymers. Melting is one, just overheating the tooth flank. Tooth root fracture from bending stress, similar to metal fatigue, but often at lower loads. Tooth flank fracture from excessive contact stress, that Hertzian stress. And then general wear or thermal overload leading to plastic deformation. The teeth permanently bend out of shape and can't mesh right.
Can you give an example?
Sure, for POM gears. At low loads, you mainly see flank wear.
Mhm.
But increase the load, wear gets worse, meshing becomes incorrect, friction increases, it heats up fast. Around 80 degrees Celsius tooth temperature, the material softens, teeth flex more, you get plastic deformation or even melting. It's a damaging cycle.
Yeah.
Wear causes heat, heat worsens wear and causes deformation.
So how do engineers fight back? How can we improve polymer gear performance and make them more resistant to wear and heat?
Several key strategies. Reinforcement is a big one.
Hmm.
Adding glass or carbon fibers into the polymer matrix makes a huge difference.
How?
The fibers are much stronger and stiffer than the polymer, and they conduct heat better. It creates a composite material. This can increase load capacity by up to 50%. The fibers help distribute load and dissipate heat more effectively. Lubrication is also crucial, but it needs care. You have to choose the right base oil that's compatible with the specific polymer. Some oils can make polymers swell or degrade.
What about internal lubricants?
Yes, the source mentions experimental analysis showing PTFE Teflon blended into the polymer matrix works well, especially with polyamide. The PTFE particles migrate to the surface during use, providing a low-friction film.
Any other tricks? Coatings? Geometry?
Coatings are tricky. Specific multilayer PVD coatings haven't proven effective. They tend to peel off because the polymer and coating expand differently, causing more problems. But yes, even subtle tweaks to the gear tooth geometry can optimize stress distribution and improve durability.
That idea of combining materials leads nicely into our next section. Hybrid solutions and how additive manufacturing makes complex designs possible. Indeed, that overheating issue is the main hurdle for wider polymer gear use. So researchers looked at adding metal inserts right into the polymer.
Exactly. These hybrid polymer-metal gears aim to combine the best of both worlds. It's a significant step for improving wear resistance and durability.
How do the inserts help with heat?
They act like heat sinks. Strategically placed inserts of steel, copper, or aluminum draw heat away from the tooth flank, where friction generates it, and conduct it into the cooler gear body. This lowers the risk of the polymer deforming or melting.
And which metal works best?
Aluminum seems most promising, according to the source. Good balance of mass, cost, and crucially, excellent thermal conductivity. It pulls heat away efficiently without adding too much weight. The visual comparisons in the research are quite telling. You see much less tooth profile deterioration in hybrid gears compared to standard polymer ones.
But there was a surprising result comparing steel and aluminum inserts.
Yes. Steel inserts actually led to earlier failure than aluminum ones in tests. It seems counterintuitive, but it's down to properties. Steel is much stiffer than aluminum, which can create stress concentrations where it meets the polymer. And critically, steel's thermal conductivity is much lower, about 6 times lower than aluminum's. So even though steel is strong, it just couldn't get the heat out of the polymer fast enough. The polymer around the steel insert melted sooner. Aluminum's better thermal performance let the gear run cooler and last longer.
But hybrids aren't perfect either. There's a stress issue.
Right. A key disadvantage is increased stress concentration right where the metal insert meets the polymer. Because they expand and contract differently with temperature changes, it creates stress at the interface.
So the ideal insert.
Ideally, you'd want a highly conductive material with thermal extension similar to the polymer. But designing that perfectly can get complex and expensive with traditional manufacturing methods.
Which is where AM comes in.
Exactly. Additive manufacturing is the enabler here. Originally for prototypes, AM is now fantastic for efficiently producing single complex parts.
How does it compare to traditional methods like cutting or molding?
Big advantages. Compared to cutting material away, subtractive manufacturing, AM produces almost no waste. It only adds material where needed. And compared to injection molding, there's no need for expensive custom molds, making it great for low volumes or unique designs. That flexibility and cost-effectiveness are huge for gears.
And for polymer gears, fused deposition modeling, FDM, is the most common AM process. Can you quickly explain that?
Sure. FDM is basically extruding melted plastic filament through a nozzle, layer by layer, onto a build plate. Each layer cools and fuses to the one below, building the part up. It's well suited for polymer gears because it works with many engineering plastics and produces relatively strong parts. Interestingly, the source notes FDM-made gears often have significantly higher load capacity than those made by SLA, stereolithography, which uses UV light to cure resin. That's down to material properties and how the layers bond in FDM.
What polymers are typically used with FDM for gears?
Common ones include PLA, ABS, polyamide, PA, or nylon, and even high-performance ones like PEEK.
And it's not just the material, but the printing settings that matter too.
Absolutely critical.
Hmm.
Things like infill percentage, how solid the inside is, print speed, nozzle temperature, bed temperature, they all significantly influence the final strength and durability.
How so?
Higher infill generally means stronger but heavier. Print speed needs balance too fast. Hertz layer bonding too slow is inefficient. Temperatures are key for proper melting, flow, and layer adhesion, affecting the material's internal structure and properties. Fine-tuning these lets you balance strength, durability, and production time. And the experimental results back this up. ABS showed the highest wear rate, making it less ideal for demanding gears. PA, polyamide, had the lowest wear rate, proving more durable.
Any surprising findings?
Yeah, one really interesting one. PA618 gears made using FDM actually lasted longer than traditional injection-molded PA66 gears under lower loads. It's pretty impressive. AM not just matching, but potentially exceeding conventional methods in some cases.
And the benefits of AM go beyond just making the initial gear.
Oh, definitely. It transforms the whole life cycle. AM allows for super efficient repair or replacement. Need a new gear. Print it on demand. Minimize downtime. No waiting weeks for a specialized part. It enables economical production straight from a 3D CAD file. No molds, less machining. And the design freedom is incredible. You can create gear shapes, internal structures like lattices for lightweighting that are simply impossible with other methods. Truly optimized designs become feasible.
When actually using AM, what's the trickiest part?
Well, first, you choose the technology, often FDM for polymers. But the second, and probably most challenging step, is material selection.
Why so hard?
Because there's a huge range of polymers and composites now. You have to carefully weigh mechanical properties, thermal properties, cost, how well it prints, and crucially, the specific demands of the application. Choosing the optimal material requires deep knowledge of both material science and the gear's job. The wrong choice undermines all the AM benefits.
What an incredible journey we've taken today. Started with the basic, vital function of gears, dug into why they fail, explored cutting-edge diagnostics like AI and digital twins, and then uncovered these groundbreaking material and manufacturing solutions, polymers, hybrids, all supercharged by 3D printing.
Yeah, it's been quite the deep dive. To recap some key takeaways, that quest for longer lifespan and better reliability in gears. It's continuous, fundamental for performance, efficiency, safety across so many sectors. And AI, deep learning, they're truly revolutionizing fault detection and diagnosis, pushing us firmly towards predictive, proactive maintenance.
And it's clear, condition monitoring needs to span the entire life cycle, right from the design phase. We also saw how crucial material properties and proper heat treatment are the foundation of reliability and performance. And while metals are the traditional choice, these innovative materials, polymers, advanced composites are really closing the gap. The source even mentioned woven fiber composites offering potentially 100% higher load capacity than short fiber ones. That opens up applications we couldn't even dream of before.
Absolutely. And finally, additive manufacturing emerges as this incredible enabler, offering speed, economy, design freedom. It's fundamentally changing how gears are conceived, made, maintained, replaced. It really signals a new era for mechanical systems.
So pulling it all together, what does this mean for the future of mechanical systems?
Well, it raises an important point highlighted in the research. While wear and temperature resistance are vital, materials for reliable gears also need high toughness.
Toughness. Meaning
Meaning the ability to absorb energy and deform plastically without fracturing. Resilience against sudden impacts or stress concentrations. It's not just about being strong or hard, it's about not being brittle.
That's a really powerful thought to leave our listeners with. As engineers push these boundaries, this blend of cutting-edge materials and advanced manufacturing like AM means we're constantly redefining what's possible with gears. So consider this. What traditional gear applications might be entirely replaced by these innovative solutions in the next decade? And what new challenges will pop up as we push these new materials to their absolute limits? Think about how future research might unlock the full potential of even common polymers like POM or PVDF in additive processes, or how comparing different AM technologies could fine-tune gear properties for even tougher jobs. The deep dive into the world of gears, it seems, is far from over.